Now you've got some idea of the four forces on the aircraft. Let's you and I talk about what actually creates the lift that makes an airplane fly. We can refer back to a guy named Bernoulli, I guess I should say, who I am told was Swiss, who did some experiments. And what he did is he forced moving air through a narrow point in a tube. Now, a narrow point in a tube is called a venturi. And he put some gauges in here, and he measured the air pressure as it went through this narrow point in the tube. Now, he found what I think is really fascinating things when he did this. What Bernoulli found is that when the air got to a narrow point in a tube, it has to speed up. And the interesting thing he found is with the gauge, he measures the air pressure where the air is going the fastest. And what Bernoulli found is at points where the air is going the fastest, the pressure is the least. There is a low pressure inside this venturi. Now, if we remove 1/2 of the venturi and take it away, you're going to find now we have an airplane wing. And you'll find exactly the same thing occurs in an airplane wing. The air going over the top of the wing gets forced out of the way. It resists compression. By the way, if you put air in a gallon jug and squeeze it, you can compress it. But free air is incompressible. So if you force air out of the way, it doesn't compress at all. What it does do is speed up to get out of the way. And Bernoulli's law says, and here's the trick, Bernoulli's law says at places where the air is going the fastest, like over the top of the wing, the air pressure is less. So over the wing of an airplane, what you really have is a low pressure area up over the top of the wing and a relative high pressure area underneath the wing. And that's that pressure differential that creates lift. That's what makes the airplane fly. You have low pressure over the top of the wing, high pressure area underneath the wing. And that pressure differential will occur anytime the air is flowing smoothly over the surface of the wing and conforming to the surface of the wing. Now let's you and I take a look at a couple terms the FAA wants you to know about. First of all, if you take a look at an aircraft wing, and if you draw a line from the trailing edge of the wing up here to the leading edge, that line is roughly called the chord line, and it points the direction the wing is pointed. Now if the wing is going this way, the wind will be coming from the opposite direction. They call that the relative wind because it's the wind relative or in relation to the wing itself. And so if the wing is going this way, the relative wind will be coming the opposite direction. Now this angle between the chord line of the wing and the relative wind is called the angle of attack. And the FAA wants you to know that, and they call that an acute angle, meaning it's the small way around, not the big way around. The small angle here is called the angle of attack. Now the FAA is going to ask you that terminology question, so let's you and I take a look at figure 1 back in the back of the book and the FAA pages back there, and they're going to ask you what is acute angle A here? Well, here we have the chord line of the wing, here we have the relative wind. That angle is called the angle of attack. So that's one of the things you need to know is angle A is called the angle of attack. Now, the angle of attack determines how much lift there will be on a wing. Let's you and I take a look at a wing actually flying in an airplane. Here's an airplane flying along, and we have it in a wind tunnel with smoke going over it. And as you increase the angle of attack, the lift gets greater. But however, I said there's only lift as long as the air conforms with the surface of the wing. Now, when you get the angle of attack so high, the air can no longer conform with the surface of the wing. And instead of flowing smoothly over the surface of the wing, it backfills and burbles and eddies. Lift is destroyed and the aircraft is said to have stalled. Now let's take a look at a close-up picture of exactly what we just saw there. We increase the angle of attack of this wing, and as it increases, we change the angle of attack. The relative wind can no longer conform to the surface of the wing, and when it separates from the surface of the wing, and then it continues and burbles and backfills and eddies, you're going to find that lift is destroyed and the aircraft is said to have stalled. Now, an airplane stalls at a specific angle of attack. The exact angle of attack at which the air can no longer conform to the surface of the wing is really designed into the wing. So an airplane stalls at the same angle of attack regardless of the gross weight of the airplane. So at what angle of attack does an airplane stall at? Always, for the particular airplane and configuration of the wing, always at the same angle of attack. So that's one of the things you need to know. Now, as you go to higher altitudes, there's thin air at high altitudes, but that thin air affects your indicated airspeed, your airspeed indicator, in exactly the same way it affects the wing. So would you stall at the same indicated airspeed at high altitude or lower? And you see it right now. The indicated airspeed at which an airplane stalls will remain the same regardless of the altitude. There's thin air at higher altitudes, but there's thin air for both the wing and the pitot tube, and they're affected exactly the same way. So it's the angle of attack that makes an airplane stall. Now, normally an airplane will stall at a specific indicated airspeed because unless you have some load factor on the airplane, G forces on the airplane, it'll stall at a given angle of attack, and that angle of attack will always occur at a specific indicated airspeed. Now let's talk about spins, and this is an interesting example of spins right here. Spins are really exciting flight. That's fun, isn't it? All right, well, maybe it isn't fun for some people, but that's a spin. Now they're going to ask you on the test, what do you have to do to spin an airplane? Well, in order to spin an airplane, first it must be stalled. So you need to know, if you want to avoid this, want to avoid spinning an airplane, you need to avoid stalling that airplane. Now they're going to ask you, when an airplane is spinning, are both wings stalled or just one wing stalled? And the answer is, regardless of which direction the airplane is spinning, to the left or to the right, both wings are stalled. Why is it spinning, you might want to ask? Well, the reason it's spinning is because one wing is more stalled than the other, but both are stalled. So during a spin to the left, the FAA will ask you on the test, how are the wings? And the answer is both wings are stalled.